Okay, so that's great. Okay, so as well as those things that we've looked at there a moment ago, linear operators, there are also a lot of non-linear things that we can do. One of those is the gamma correction. Okay, no, it's called gamma correction because they use the symbol gamma. Where exactly they decided to use that, I don't know, but that's what they do, and it's been used ever since. They call it gamma correction. It's called correction because of the fact that in many cases this is trying to undo a non-linearity that has happened somewhere, and they want to bring it back to something that's linear. Now, this is something that's going to pop up again and again and again, this idea of straight lines, linearity, mathematical rules for linearity and so on. And you're going to find that, you know, that entire subject that you did on linear algebra, the clue is in the name, requires things to be linear before they can actually do all, before you can use all of those tools that you've learned. So an awful lot of this module we're going to find is trying to get things to into a linear zone where we can actually use them and use all the tools that we know, or otherwise things get into a bit of a state. In this particular case, what we're doing is we're saying we take our image brightness value, but we don't change it in a linear way. So if we go back to our example back here, rather than it being in a straight line, we might have something more like this, where it will go up and round like that. Okay, so it will go up in some form of a curve. Now, as I say, a lot of systems have these non-linearities by virtue of just the way they are, and we'd like to be able to undo that. So we'll often try and do that curve in order to undo something else. So in most camera systems, the mapping from the input brightness value that comes in to the actual pixel values is a non-linear one. It just doesn't operate perfectly. So the gamma correction can be applied later to undo this. Typical value of gamma would be 2.2, is well suited to most digital cameras, and you'll also find screens and monitors also have to undergo some sort of gamma correction as well. I know that a number of years ago Apple decided to change their gamma value, and Mac users refer to it as the Great Darkening, because it changed it to a value that everything, if they used their standard values that they had been using up until then, all their screens looked darker than it was, and it was obviously a decision that they made. The two, if it's a value above 1, so from 0 to, help now if I was writing in black, from 0 to 1 will make the image brighter, and from 1 upwards will make the image darker, and that's because the gamma is in the denominator there in the exponent. Okay, so that will be the effect of it. Again, worth your while playing around with those values, maybe getting a computer program and actually having a look at the effect that has. I'm mentioning to you lots of things that I'd like you to do in computer programs, and what I definitely want you to do this week is to set yourself up with a Python environment, and if you look up OpenCV, it's a library for Python, and it will allow you to, and you'll find loads of examples. Nearly all of these functions will be named, and you can just go and find the computer program and run it and get it running very, very, very easily. So I do want you to play about with that, because most of the assignment work in this module will be based on maybe some Python programs. I won't be too concerned about the program themselves. I just want to see the results and how you communicate those ideas. But we'll come back to that a little bit later. But this week I do want you to set yourselves up with a Python environment and try and get some computer programs running. So the next thing we're going to just briefly touch on is color transforms. So you've heard of RGB, I assume most of you, if because I asked Shane Gilroy the other day and he said you've all heard of RGB, so I'm not going to hear otherwise. So red, green and blue is normally the setup of most monitors, and it's also what would be used in most camera systems as well. We have 3 pixels, red, green and blue, in order to give you the different possible color values. So we could consider these 3 separately as 3 separate grayscale values, where each one of them can go from 0 to 255 if it's 8-bit, and treat them as 3 separate images. So if we decide to brighten each of these individually by the same amount, so in other words, if those functions that we looked at earlier, if we decide to brighten the red, the green and the blue by the same amount, what will be the effect. And what you'll find is you'll be in for a bit of a nasty surprise, because while as well as brightening, we may actually get quite a bit of colour drift. So the things will not end up being the same colour as they should have been. So it's not that everything has just got brighter, it's actually that things have changed in colour. And so you might have things like skin tones would appear an unnatural colour. They wouldn't appear the colour that they're supposed to be. Okay, so the problem here is that the colour channels are highly correlated with each other. In other words, they have a real dependence on each other. So treating them independently can have poor consequences. The better option here would be to try to separate brightness from colour. And there are other colour spaces other than RGB that we can put it into in order to separate those out. There are various names because various different researchers and so on over the years have come up with these different ones, or different companies or standards associations and so on. So YUV is one of them. YIQ is actually very similar to YUV, and there's another one called CIE Lab where LAB is actually the three constituents of it. In each of these cases, the Y in this one and the L in this one refers to the brightness value alone. So basically that's your grayscale image, and then the other two components hold the information on the colour. And indeed, back when colour television first came in, they needed to make sure that colour TV's signal worked alongside all the black and white TVs that were there, so they couldn't just change them all to RGB. They had to come up with other systems, and this is where a lot of that stuff comes from. So we would then, what we'd then do is we would only apply the brightness change to the Y channel or the L channel if we're using LAB, and then reconvert it back into RGB. Okay, so we may of course want to change the colours of an image. Most often in pre-processing, this would take the form of colour balance correction. So again, I'm using that word correction rather than enhancement, because what we're basically saying is we want to correct for some colour that's gone wrong in our, in our capture, our image capture. So a problem exists that different light sources have different colors associated with them. Our eye is extremely good at being invariant to those. We see white as white no matter what. But if you take a photograph of something and you don't do any color correction, you'll find that your whites and your grays tend to take on different color tones other than white and gray, other than that neutral color. So sunlight, for example, has a blue tone, whereas fluorescent LED, camera flash and tungsten all have different colours associated with them. And if you have any sort of near to high-end digital camera, you'll normally see a setting on it there where you can change it to the different settings, whether you're shooting inside or using camera flash, or if you're shooting in a daylight setting. As well as that, most digital cameras will have an automatic white balance, which is where they use some sort of computer vision algorithm to try and determine what their colours should be. So they're normally looking for something that's a neutral, that should be a neutral colour and isn't, and what they'll try and do is they'll try and move that in that direction. So in many cases, we're not just correcting for one particular colour problem. So if we were just out in daylight, that would be fine. We're only dealing with daylight, and that would be a kind of a blue tone, and we would just correct for that. And that's, we'd have a fairly good idea how to do that. But what happens in many cases is that, it's coming towards dusk. We've got blue reddish, which is now moving towards more reddish light because of the sunset. And then you've got street lights coming on, and they might be tungsten. And you've got all these different competing colour values that are going on there. The human eye is very good at tuning those out. If we take an image, we might want to correct them so that they look right for a human viewer. But the other thing is that if we're dealing with a computer vision algorithm which has to make a decision about what it's seeing, and if it makes that decision based on a colour, we could send it the wrong direction if it's got the wrong information, if we haven't done that correction. So in these cases, we'd like uniform grey parts of the image to be grey and white parts to be white. And there are many algorithms for doing this, from individually modifying each of the channels separately to converting to a colour space that separates out the colour, and then making global changes that move the grey parts of the image to values in that space that have zero colour. So we move at that, and then we move everything else by the same amount. Every other pixel moves in the same direction, and then what we do is we convert back to RGB. Okay, it's a very specific end of image processing, but it's one to be aware of. So If we want to convert from one color system to another, there's generally a set of matrices that we would use, and you normally you'll find them in many different textbooks and so on. So if you want to try and convert from, let's say, from RGB color to YIQ, you can try it with the following values: an R value of 126, which is kind of a middle brightness value; G, which is the green, is 120, which again is a middling bright value; and B is 200, which is quite a bright value. So the matrix C is a linear transformation. So there's that word linear again. It's going to come up again and again. Get used to it and try and find out as much as you can in the meantime on it. And we're going to do a linear transformation from RGB to YIQ, and we use a matrix C here, which you can see the values that we've included there. Now immediately what you notice here is that there are some negative values in there. And what that means is that when we convert to this YIQ space, we may well end up with negative values. Now, I said we could only have values between 0 and 255. That's certainly the convention with RGB images, but it's not necessarily the convention with other color spaces, where sometimes they do have negative values, so they might vary either side of 0. So if we take just 1 pixel from our image, which I've given a vector, so it's got 3 parts to it. These are not the coordinates; these are the 3 brightness values of the red, the green, and the blue. Okay, so it's that in that third coordinate there, and it's got 3 values associated with it. What I can do is I can pre-multiply here by C, which you've done plenty of in your linear algebra subject, I've no doubt. So what we do is we pre-multiply our vector there with the RGB values in it by this C matrix, and you know how to do this. You take those 3 values, multiply them with those 3 values, and add up the result, and that gives you your result here, and so on. You can see these negative values here. What's going to happen to them? You're going to end up with some negative values over here as well. Okay, so that's our result there. You'll notice that those are integer results. You're unlikely to get exactly integer results, so what you've got to do is you've got to round up or down to the nearest one if you're dealing with a digital image, and that's just to be aware of that. So once you round up and you round down, you've lost some information again. You had probably already lost some information in digitizing these numbers in the first place. Now you've lost it again in doing the color conversion. How do we get back from this? Well, you can assume that C matrix is invertible. I'm sure you also know how to invert a matrix. I won't be getting you to do too much of this actual, trying to invert a matrix or otherwise on paper, unless it was maybe a 2 or 3, 2 by 2 or 3 by 3 matrix. That's fairly doable. But in actual fact, if you use Python, and there's a particular library called NumPy, which is NUMPY. How many of you are familiar with this? Just a Y or an N, NumPy? Okay, so a good few yeses there. So NumPy just stands for number, and obviously the pi is related to Python, and it will do all your linear algebra sort of stuff for you. Okay, so there will be functions in there for inverting a matrix, functions in there for getting the eigenvalues or eigenvectors of a matrix, all of that sort of thing. So get that library along with your Python and start looking at examples online, examples of programs, and just get fiddling about with that and get it working. Why did no one tell you that last term? Unfortunately, I didn't have you that last term, Niall. But in fairness, you do need to know about how to do these things on paper before you do them in a program, because you always need to be able to. You can't just trust that your program works. You need to be that bit more sure of it. But yeah, it probably would have been a bit of a help. Anyway, I'm telling you now, so make sure you get up and running with it. Very powerful tools there, and so you can do all of that. So you could get the inverse of this, but the chances are that you'll find a textbook that will also have the inverse matrix here as well, and you just pre-multiply it by this one here, and that'll give you your result going back the way. Okay. Now, I mentioned earlier compositing and matting. So matting refers to extracting an object from an image. So let's say, for example, we have an image and we want to try and remove a person from it, or we want to try and move a vehicle from it or something like that. So we want to separate it out from the foreground. That idea is called matting. Compositing then refers to the idea of inserting an object into another image without noticeable artifacts. Now that word artifacts just means things that appear in images that make it obvious to a human being that something's not right there. There's something a bit strange. Okay, so it should not be obvious that when we composite something into an image, it should not be obvious that it was not part of the original image in the first place. Now, blue and green screens really help with this, because we can basically separate out that color, look for that color and say, okay, wherever that color is, that's our green screen, and we're going to replace that with something else. And that can work very, very well. And they use that a lot in the film industry. Some terms to be familiar with here are foreground, background. So in other words, the objects generally that you're trying to remove or put in, they're known as foreground, and then the background is all of the rest of the image. There's also the alpha channel, and we saw that formula earlier. There it is there. That formula earlier that has that alpha value in it, and that's the very basic way of doing that. And then they have much more sophisticated ways. If you're particularly interested in compositing and matting, I've left some of the original papers by a guy called Jim Blinn from the 1980s, who pioneered a lot of this work. I've put them up on Moodle there. You can have a read of them. I'm not insisting you have a read of them or anything, but I want to put up each week some papers that are related to the things that we're covering. So it is worth your while maybe taking a quick look at that, just to get an idea of how these papers are written, and maybe then you could try and implement some of that stuff in Python if you're feeling that way inclined. So alpha is a fourth channel that is added to our 3-channel image. So we've got red, green, blue, and then this alpha, and it's in this range. So again, we've that in, which is an element of, but we can just say in the range 0 to 1. So we decide how much of what percentage of our alpha is, or what proportion of our image is going to be included in the composite image in the end. So this is the transparency or opacity at each pixel. So in an alpha matted image, a pixel that is definitely in the foreground object, we want to take out of the image, it will be set to an alpha value of 1, which is fully opaque. You can't see through it. Pixels that are definitely outside the object, in other words, that are part of the background, they would have an alpha value of 0. Which is fully transparent. And then when the boundary of the foreground object and the background is not distinct. So for example, if and you'll see this a lot, if a hair is sticking up in the air or something like that. I thought my head was going to freeze in that position for a minute. But if you've hair sticking out and so on against the background, those hairs will not be the width of a pixel. So they'll darken the pixel to some extent, and you've then got to make a decision about how much of that alpha value you're going to include when you're putting it into the next image. And you've got to worry about the fact that in the first image it had a different color behind the hair than it has in the second one, and trying to recover that situation. And that's where the real difficulty of trying to get this thing to look realistic occurs. So then to composite the object onto a new background image, we use the following equation, which is called the over operator. C is equal to, so C is our composite image. It's equal to 1 minus alpha times the background image plus alpha times the foreground image. And of course, if alpha is, as I say, a number like 0.3, 1 minus alpha is going to be 0.7. So it's just the proportions of each of the pixel of the background and the foreground that we're going to include to come up with our composite image. So depending on the application, we sometimes pre-multiply alpha F and store it as an alpha matted image. So you'll often see images that appear to be kind of transparent behind them, or they're not a full image, and it's because they're already in this format ready to just slap onto the background image that it's going to go into, rather than trying to take the original image and trying to slowly take each bit out. So you'll often have that as an intermediate image, as opposed to just starting with F and including that in the overall function. There are lots of other functions other than the over operator. Obviously, that's I'm only showing you one. That'll suffice for what we want to cover here. Now, contrast stretching, which I would definitely consider. Well, actually, would I consider it an enhancement or a correction? Is difficult to tell. The brightness and the gain that we mentioned earlier are useful but require human judgment, and in computer vision we must always consider if the values can be automatically determined by some mechanism, and contrast stretch is one option here. It aims to make the most use of the dynamic range available, for example in an 8-bit image. So if an 8-bit image is 0 to 255, we would call that our Vmin, which is our output values, and Vmax. Find the darkest pixel in the image that is actually in the image at the moment, which we can do via things like the histogram and so on. We can find the darkest pixel, and we would call that Umin, and then find the brightest pixel, and we call that Umax. And what we want to do is we want to stretch our pixels so that they use the full range of values that are available. Okay. So imagine that I set an exam for you guys, and everybody gets between 50 and 60. And what I then decide to do is say, well, no, I'm not interested in what you know. I'm only interested in how you applied yourself relative to each other. So what I could then do is I could take the ones at 50 and drag them all the way down to 0, and try take the ones at 60 and drag them all the way up to 100, and we would then get a much better spread, and we would see how students performed relative to each other. Don't do that with your exam results, by the way, just in case you think I do. But you can see how, in terms of an image, that this would actually really improve the situation in many cases. So if we go back to our example here, this here would be as follows. You can see here that I am not using any of the pixel values between 0 and about 35 there, maybe 30. Okay, I'm not using any of those values, those brightness values. And I'm not using anything from 200 up to 255. They're all being wasted as well. So what I would do is I would try and stretch those that way and stretch this that way, and everything else linearly in between. So what that would amount to is I would draw a straight line here up to there. And that means that the first number in here, the 30 pixel, it immediately gets mapped to 0. And then what I would do is I would have another value up here. So we'll just follow that up to about there. And I'll draw a straight line. Okay. And we already know how to do this sort of thing. This is basically just going to be multiplied by some value here. And then what I would do is all the numbers in between 200 and 255, and there are no pixels in that value, they would automatically get moved to 255. So this number here at about 200, it would get moved to 255. The one a bit below it would get moved to maybe 254. But we get this greater stretch in between the two. And what that would mean is that in terms of the image, the blacks would get blacker and the whites would get whiter right up to our limit, and we'd use the full stretch of the information that's there. That's certainly very good for a human viewer, but it may also be useful in separating different parts in terms of a computer vision algorithm. Going back to my example where I said that the different subsystems of the car will all have to rely maybe on the one image processing pipeline coming up to that point, or maybe 2 or 3 image processing pipelines, but there's a good likelihood that they will have to share that image processing pipeline. So it would make sense that if you've got a dull day out there and you're not seeing a huge variance in terms of the pixel values, that you could do some sort of a contrast stretch, and that would separate the pixels out a little bit further in order that you would make the best use of the numbers that you have. So this is the formula for it. It looks a little complex, but actually I do this with my second year students, level 6. So you should be well able to handle it. It's just 3 different parts to it. So this is more like a computer algorithm really, rather than a maths thing. So if our values are smaller than Umin, in my example there, anything from 0 up to 30, my Umin would have been that 30 value, that lowest value there. Any of those, they immediately go to the Vmin value, which is 0. Anything above Umax, which I said there was nothing really above 200, so we'd maybe set that to 200. Any brightness value that's above that immediately gets set to our highest value here of 255. And all of the numbers in between get multiplied by this range. So we stretch the range there. And you can think about that. Basically all this is saying is Vmax minus Vmin, that's going to be 255 of a difference between them. U to Umin, well, that's our current value that we're testing. We subtract the bottom value from it so that we end up there. That's kind of like our y-intercept. It's not quite your y-intercept, but it's similar to it. And then what we say is the range here. And of course, our range would have been somewhere from 30 up to 200. So we have a range of about 170. So therefore, immediately we have our 255 over 170 is giving us our rise over our run. And we're then saying, well, how far are we above our smallest value? And therefore, how far are we up that curve that we get a result? And once again, as I say, we could write this as a computer algorithm and do this calculation every time for every pixel, or we could do it once for our 255 or 256 different color brightness values, and then just set up a table so that we can just pluck out of that table. So each number that comes in, we have a number come straight out the other side. Because otherwise you'll be dealing with floating point numbers and then trying to re-quantize them and all sorts of things. So it really depends on what it is that you need to do as to which way you would go about that. Okay, and we can take this to its logical extreme. We can say that rather than just stretch them out, let's say that we want the same amount of pixels brightness values in each brightness value. Okay, so in other words, throughout my image, if I've got 10,000, I'm going to make the numbers easy on myself. Let's take 200 and 2,550 pixels in my image. Let's say it's that. So I would then have 10 pixels in each of the brightness values. So my histogram would look something like this. So I'll just draw here. And we'll take this to be 0 and this to be 255. And what I would get is I would get a uniform distribution all the way across here from there to there. And hopefully you'll be seeing all about uniform distributions and Gaussian distributions and things like that in your statistics and probability subject. So that should be a straight line. I haven't drawn it perfectly straight. So the idea would be that we change our image in such a way that we have an equal amount of each brightness value within our image. Okay, and you can do that with a thing called the commutative distribution, which would take me about 5 minutes to go through. But the basic thing is that each value here, in other words, if we're trying to find out what our brightness value should be for an input brightness of 10, what we do is we go through our histogram and say, well, how many brightness values had we at 0? How many had we at 1? How many had we at 2? And we add up all of those and divide by the total number of pixels. And that will tell me how many or what brightness value I should now be at for my brightness value of 10. So what it will move to. And we continue on the way. If we do it by the manner that's shown here, this is quite expensive because for everything that we do, we have to add up all the results. Instead, what we do is we take the last value that we figured and we just do a quick calculation on this new value, and that's a much faster way of doing it. I'm not going to go into it in any more detail than that because there's more important things to cover, but just be aware of that. And you can also, you can quite easily test that in Excel or something like that and just see that you can follow exactly how it works. I've tried this and I did this again. No, admittedly I did this in Photoshop, so I just clicked the equalize button or the equalize menu option. So I don't know that it absolutely followed this particular function here, but it will have done something similar. And what you can see is, firstly, my histogram now has gone all the way from 0 to 255, but you can clearly see that this is not a straight line across here. It's still up the way. Now, part of the problem that's happened is that what has occurred is that because of rounding errors in this calculation, we've in certain cases rounded to certain integers far more often than we rounded to other integers. So you will see over a short range, you will normally see one pixel that's got a load of values in it and another one then that has absolutely 0. So we can see plenty of these pixels have absolutely no pixels at that brightness value, and then other ones beside them have a very high value. So we haven't separated them out very well. So over a small period, if you looked at over maybe 5 pixels and then you looked at maybe 5 pixels up here, you would find that actually they have roughly the same amount in them. So that function will work quite well. Normally, histogram equalization does not look nice from a human point of view, although it's actually done a reasonable job on this photograph. This looks a lot sharper and it's got more contrast in it. That's probably just from the spreading out of the values. But histogram equalization can be maybe useful if you want to get the maximum amount of use out of your pixel brightness values. So it may have different uses in different places. Okay. Now, this brings us on to the idea of linear filtering. Up to now, we dealt only with the situation whereby we dealt with one pixel at a time and we did some operation on it. Now what we're going to say is, well, we're actually going to deal with the current pixel and some of the pixels around it, its neighbours as well. And we're going to make a decision based on the clump of them all together for each output pixel that we get. So the logical progression from point operators is to use multiple pixels to produce the processed output pixel. This normally takes the form of using a neighbourhood of pixels to produce the output pixel. So n by n, where n is an odd number, are the normal shape of these. So 3 by 3, 5 by 5, and so on. 1 by 1 is just a point operator, so it doesn't count. So you've got 3 by 3, 5 by 5, 7 by 7, and so on. Once they get much bigger than that, they become very heavy on processing power. So as the name suggests, these are linear operations. So again, rules of linear algebra will apply, which means that the order in which they occur doesn't matter. So this is some of the rules of linearity. We can do the things in any order, and there's rules like homogeneity and additivity. Again, if you haven't come across those, do go and look them up because they will matter from time to time. Homogeneity is about being able to multiply by a constant and it not having an effect, and additivity is about being able to add things together. So if we add things together in an input, it's the same as adding them together in an output. Once again, this is in pure mathematical sense. So going back to my first slide of the first part of this lecture from the beginning of the notes, there's a difference between the mathematical model and the computer model that we will build, because our linearity starts to break down when we start changing things to digital, and we have to have round off errors, and also we have a maximum and a minimum value that we can have within our image. The other problem that we face is that these linear operators, if we're trying to figure out a value for a pixel and we have to take all the neighbours around it, what happens if it doesn't have neighbours on one side or the other? Okay, so you can imagine like a house on the end of a street doesn't have neighbours on one side, and if we're making some decision based on neighbours on both sides, what exactly happens there? Okay. Could I just quickly get a sense, yes or no? Convolution. How many people are familiar with the idea of convolution? Yeah. Okay, so I think that's most people. Enough that what I'll do is maybe try and get you one or two resources, guys, just to get you to look at that separately, because I think most other people have done them. Now, correlation and convolution are two very alike mathematical operations. There is a strict difference between them in that convolution is flipped left for right and upside down. But actually in many of the operators that we're dealing with, because they are symmetrical in all directions, that really makes no difference. Correlation is, strictly speaking, in an image looking for some pattern, whereas convolution is trying to change the image in some way. How many people have heard of convolutional neural networks, or CNNs? Okay, so I think most people have heard of those. Now, they use that word convolution, but in actual fact, in most of the image recognition ones, what they're actually doing is correlation. Now, the strict difference kind of tends to come in things like digital signal processing, but for a lot of computer science and so on, they just have that idea of the thing sliding in different directions. They call that convolution, and they don't really care, and it doesn't matter what's in there, and it's going to learn. Because the convolutional neural networks learn the weights that go into them, it doesn't matter as much to them. But strictly speaking, they're looking for patterns, as opposed to convolution, which would normally be the link between an input signal and an output signal, and as it goes through some sort of system. So this is the mathematical description of them. So it's basically what you're saying is you're taking an image, and you're taking this operator that we have, which will look, it's like a small little mini image. You'll see examples of them in a minute. I'll show you an example if I can find one. There's an example of one, so we can see that it's like a small little image of maybe just 9 pixels. And what we do is we multiply those by each other, but we've got to multiply them by each other in each of the different positions that they're in, and then add up the result. Very quickly, what I'll just show you here. as an example. So that disappears if I don't have it. Okay, so we've got some sort of a 9 by 9 here, and let's say, for example, that I want to do an operation on this image over here, which is, this is our image over here, which is just a bunch of numbers. Now I want to find out the result if I'm in this position in my new image, not in the current image. What I do is I take my operator and I land it centered on that pixel there. Okay, so I land it centered on that. I multiply each of the numbers by the number that's under it. I've them on top of each other now at the moment, so you can't quite see the numbers. But I multiply each of those numbers and I add up the result, and that gives me one pixel out. To find out what the next pixel is going to be, I move it to the next position and I do the same thing again and multiply by all its neighbours. And like I say, sorry, I didn't actually click off that for you to see that. So I just move it to the next position or move it again, and so on. Okay, I can see I've lost a bit of my thing, so I'll just grab it again. Now, what happens though if I'm off the edge here, and you can see the problem that I'm going to have there. These ones are not multiplied by anything. Okay, these ones are not multiplied by anything. They don't have any neighbours, and you can see these sort of issues that we're going to end up with. So this idea of sliding the thing across the image and getting each value as we go, that's convolution. Okay, and we can do it for correlation as well, and that's what this shows us mathematically. That's the symbol for it, by the way, the little star, and correlation is usually shown as that, but not always actually. So if you've taken a DSP class, you've probably come across this. How many people have done DSP? Can I just get a digital signal processing? Okay, so we've, about kinda. Okay, so Colin, I'm putting you in the yes for that, just because I want to make up the numbers. So in digital, so about half and half. In digital signal processing, you probably came across a thing called an impulse response, which is how you would describe filters and things like that as to how they would respond to a signal. That was in one dimension. So in other words, we have a signal like an audio signal coming in, and then the impulse response would say how it responds to that. What we have in this situation is a thing called a point spread function, which is the same as an impulse response, except that it has to be in 2 dimensions. And so what it's really saying is, how does a single point, spread out to the values around it? Okay, so this is sometimes called a point spread function. And again, it's related to convolution and correlation. So I've mentioned the border effects are a bit of a problem. And there are a number of well, there's no perfect solution to the border effects. What we can do is, when you get to the border, normally within a computer system, if you get to the border and you don't multiply it by, you'll cause an actual memory fault within your computer program. So you've normally got to deal with it in some way where you don't do the calculation, or you put some numbers in as padding there in its place. So maybe off the edge of the image, you might put a row of zeros, and therefore nothing gets added in. So that's one way of dealing with it. You might clamp it. You might just take the outside edge of pixels and make a duplicate of that around the image. So that's another thing. It's called clamping. You might wrap the image. In other words, say if I go off the image in one direction, I take whatever value is on the other side of the image. So if any of you remember the 1970s and 1980s computer games, where you had one screen, and if you went off the screen one side, you came straight back in on the screen on the other side. And it's a little bit similar to that. You could also mirror the pixels. So whatever pixels are on one side, you do a mirror of them coming off it. So there's loads of different ways that you have of dealing with these effects, okay? Sorry, Niall, if you had a question there, go ahead. I seen you writing. No, you're fine. Okay. Always ask them on the forum later anyway if there was something that you felt you missed. So there are lots of these, and the first one we're going to look at is blurring an image. And you might be wondering, well, why would I ever want to blur an image? Surely it's the opposite we want. But actually, we'll find later that blurring images is very heavily used when we're trying to deal with noise in an image. So that's why it's a good idea to look at it. The simplest type of blurring is called a box filter. It's a very simple filter. It's the same value in every one of its places. Okay, so basically your current pixel, which is the one in the middle, is treated exactly the same as all its neighbours. And so this is a standard average that we're going to take. So even though this is the position that it's going to end up in, we also take all the other ones as similar. You can write this as a load of ones and just by 9 there as well. The reason we have to end up kind of with a value of 1 in the end is that if we start multiplying these by the pixel values, we don't want it just getting brighter and brighter and brighter. So if this was a number greater than 1, it would get brighter and brighter, and if it was a number smaller than 1, it would get darker and darker. So this is averaging at its most basic. You take the current pixel and the 8 surrounding neighbours. So these are each of their neighbours that it can have. Okay. And you add up the sum of these pixels and divide by 9, as there are 9 pixels altogether. So that's the simple box filter. And that will do a blurring. Not a great one, but it'll do a blurring. You can do a weighted average. You can decide to say, well, I'm going to give slightly more weight to the current pixel versus the ones beside it. Now, we'll be looking next week at the effects that these different things will have on noise and different ways of doing it. But for the moment, you can just see that if our current pixel value is the one is the position where we're going to bring it to in a new image, you want to take it as more important than the ones around it. So a very simple way of doing that is just give it a value of 2 and everything else a value of 1 around it, and divide by 10 overall, because if you add up all those numbers, it comes to 10 in the long run. And you can have loads of configurations of this. This is one example called the bilinear. This one's given 4. The neighbours on this side and this side are given 2, and the neighbours out here, because strictly speaking, these are considered slightly further away than these neighbours, and they're given a value of 1. Okay, so you have a value of 1 in each of those. And basically remember, this goes around the image and operates on every pixel. Now what that means is that for every pixel we have to do 9 of these calculations to get a new value. If you add up all those numbers, they come to 16, and that's why we divide by 16. Now, Gaussian. How many people are familiar with the term Gaussian? I would hope everybody, but maybe not. Everybody, don't anyone write no. Great. Okay, so you know the general shape of a Gaussian, right? It's a general bell shape, and in 2 dimensions, this kind of, I don't want to use the term Mexican hat, because that is sometimes used to describe some of these filters, but it's not the same as that. But it's kind of like it's sloped down on every side. Okay. Now we can. If you try and approximate that with just a 3x3 filter, you're only going to get the central point and a set of points around it. So it's really not going to do a good job. This 5x5 one is quite useful, and even better is the 7x7 will do a fairly good job. But once again, I want you to think back to the issue of, okay, mathematically a Gaussian is quite simple. You can describe it with just 2 variables. Or maybe more if you're doing it in 2 dimensions, but you can actually get away with just 2 variables. Okay, so that's not to say a Gaussian, despite the fact that it shows up in the real world all of the time, it's still a very simplified model of the real world. This is a simplified approximation of a Gaussian, so therefore it's not the same as the mathematical model, and also not the same as the real world. But it's pretty good. And so what this will do is it'll take much more precedence or priority for the central pixel. We get fairly high priority for these nearest neighbours, and a little bit, because these are on a diagonal, they're a little bit further away, and you can see then how these numbers all drop the further away that they get. And this kind of approximates that shape that we would get from a Gaussian. I say kind of, you know, we can only get as close as we can with integer values and so on. If you add up that total, it comes to 256, and hence that's why we divide by 256 there. These we'll be talking more about the next day. These are the horizontal and vertical Sobel operators, and keep going there, Niall. I'm paying attention there, so I'll see when your question comes in. These are called the Sobel operators, and what they will do is they will find edges in images. So where there's a very sudden change from bright to dark or dark to bright, these will generally find it. So this one over here will find the edges that are in the horizontal direction, and these in the vertical direction. Why only integers? No, it's actually a very good question. So this comes down to microprocessors. I mentioned there a while ago that you know, the transistors that make up microprocessors, they can only handle ones and zeros, and you've got to have loads of them in order to handle any large number. So if we have floating point numbers, the number of combinations becomes so large so quickly that even when we use floating point numbers in computers, we're still limited to the gaps in between them. So the problem is that integers are very, very fast to do calculations and so on, right? And then when you're storing things in as brightness values and so on, your monitor there in front of you, it can't really see the difference between tiny values, so it makes perfect sense to just store them as integers. So it's much more conservative on memory, it's much more conservative on processing power, and hence that's why we go down that route. And it's even more so when you consider the application that you're doing on this master's, where you're really constrained, and that's more of our job nearly than anything else. It's trying to find the good computer model that's good enough to do our different jobs. So that's the reason for the integers, and it's a good question. This is the Laplacian. How many people have heard of the Laplacian? You've heard of Laplace and Laplace transforms, I've no doubt. Have you heard of this operator called the Laplacian? Okay, so we're getting a good few no's, a few yeses on it. Okay. Yeah. So basically what this is we get the second derivative. So we get we differentiate, and then we differentiate again. So it's the second derivative. So normally the first derivative file tells us the Vin has seen it in fluid dynamics, it would certainly come up there. And gradients and so on would certainly come up. So when we differentiate, we find the slope of the tangent to the curve, and then if we differentiate again, we tend to find these kind of zero crossing points or whatever. So it's the change in the change, okay? And what we have here is we have partial differentiation. So what we're looking at is the brightness value, but I want to find the second derivative in the direction of the x coordinate. And then I want to find the second derivative of the brightness in the image in the direction of y coordinates. So how brightness changes throughout the image is what we're looking at here. And if we add those two together, we get a thing called the Laplacian. It has a particular shape. And this is the one that looks a little bit more like well, actually, I don't know is this quite the Mexican hat either, but it has a particular distinctive shape. But the thing is, you can see here that what we've done is we've approximated it, and this is a really, really simplistic approximation of just a 3x3, but this will kind of show us our zero crossings in every direction. So if we take highest priority for our center, and then we look in the negative direction in all cases, we're going to find where there's been that change there. Okay, so again, the Laplacian is a very, very good operator when it comes to things like edge detection and so on, and we're going to see how it's used next week a little bit more, but just want to make you aware of it. Again, we've got a very simple operator there which we can apply in very fast. It's not the exact same as what our mathematical model would like us to have, but it does a good enough job in most cases to give us what we want. And remember that in many of the cases, what occurred is that these were originally developed when computers were, in the 1970s and 1980s, computers were very primitive, and they really had no option but to be frugal with the computations that they did. That's great for us, because even though things have moved on hugely in the last 20 or 30 years, we have a separate problem now where we're now trying to be really efficient on embedded systems and not use as much energy and not use as much computation, because there'll always be more computation to do, and therefore it's great for us to be able to go back to these old algorithms which were already very efficient in the first place. So not all noise has a Gaussian or a uniform distribution. So noise that occurs in image that we might be trying to get rid of, it doesn't all form a nice sort of Gaussian thing, Gaussian distribution. So shot noise, for example, is noise where there are occasionally very large values all of a sudden out of nowhere. By very large, we mean well outside the range of a standard deviation of what we would expect from kind of Gaussian noise that might be in the electronics and so on. Regular blurring with a Gaussian filter will make a change here, but one large pixel value that's way out will cause problems and overpower all of those close by. So let's go back to our Gaussian here. Imagine that, and remember that what's going to happen is this is going to be placed on top of each of the pixels, and the 5 by 5 around it are all going to be multiplied by their values. So we're going to do 25 calculations here for every final value that we have. Now imagine we've got all low values of pixels. For example, let's say we've a 6 and a 5 here in this, and an 8 here and a 4 or something like that. And then all of a sudden here we've got shot noise. We've got a sudden very large brightness value, and it's of 150. So what's going to happen now is we're going to have a 24 multiplied by 150. This value in here in the center might only be a 4 multiplied by 36. This one absolutely overpowers everything else, and therefore it doesn't really smooth it out. It ends up kind of giving us some it will smooth it a bit, but it will still be there, and it'll actually probably end up looking a little bit worse. Okay, so so rather than being removed, what it'll do is it'll widen it out, and it does bring it down a bit in value, but it'll still be very, very visible. So what we could do here is, rather than use the mean value, which is the average value of the set of pixels within that what we call that receptive field where it's looking, what we could do is we could use the median value. So median values deal very well with outliers because we take the central value of what we see most often. Okay. So if we sorry, the median, to explain it, if you haven't come across it before, we line up all the different values we have and we take the central value that's there, and that's much more likely to be within the range than one outlier, which could be way out and would affect all of our scores. So for shot noise it works well, but it's not an efficient way of averaging ordinary Gaussian noise. So we've now got these different operators that work very well with different noise, and the problem is we don't always know what we're going to be dealing with, so that can be a bit of a problem. As well as that, this is a non-linear operator, so it's not always reversible, and it requires more of an algorithm than a simple calculation. Okay, so to combine the two filters is called an alpha trimmed mean, which can be used. This does a mean on all the pixels apart from pixels that are outside some fraction. So what we can do is we can line up all our pixels, remove the ones that are way outside the range, only take the ones in the middle, and then do an average on them. So that's another way that we have of going about trying to deal with both situations at once. Now, we're up on the time, and have anybody heard of the bilateral filter? I'm just curious. Only 3 slides, but it would take quite a bit of time. Okay, so that's all no's. Okay, now I'll just give you a very, very quick 2 or 3 minute explanation of it, because it's not vitally important. I've kind of put it on here in the end, but it is a much more modern filter than the other ones, right? Now, what it's basically saying, one of the problems that we land ourselves with is that all of those previous filters that we could use to try and get rid of noise, the problem is a legitimate edge, a set of edge pixels in the image, and edges often tell us quite a lot of information. It will blur that edge as well. Okay, it doesn't care there's an edge or noise, it just gets rid of it altogether. But the thing is, what the bilateral filter tries to do is it tries to say, okay, I'll do my standard Gaussian. In other words, that I'll take my current pixel, and the further away pixels are from me, I'll take less of their information. I won't take them as much into account. So that's no different. But what I'll then do is I'll multiply it by the brightness or the range of the pixels. So if my current central pixel value is of a certain value, let's say it's 100, I might take high priority for any pixels around me that are anywhere up to maybe 110, and this. It doesn't just stop at a certain number. It has a Gaussian distribution away from that again, so it quite quickly drops off. But it might say, well, a brightness value that's quite close in proximity to me, to my current pixel, but is maybe up at 150. That's probably a legitimate edge. It's probably not. It's not a bit of noise, and so because most noise is Gaussian, I'll apply a Gaussian in the in the Z direction, or in the brightness direction as well, and I won't take account of those. So here's what it looks like. There's your image. There's this thing called this filter, the W, and it's made up of 2 parts. This part is very much your standard sort of Gaussian that we've looked at before. So in other words, it goes off in different directions. It's a little bit different than that, but quite similar. And then this one looks at the pixel brightnesses at the different positions around it. And what it basically says is, If they're very, very different, I don't take them as much into account as if they're quite similar. So if we've noise there, it'll have a small bit of a difference, and I'll be much more reticent of that than large differences, which are likely to be edges. So it's a very, very powerful filter. The maths of it looks very complicated at first, but actually, when you get into an understanding, it's not too bad. That said, I don't know that it's absolutely vitally important for me to extend the class for another 20 minutes trying to go through it all. So if you do come across it again, and you'd like to know a little bit more about it, I can always do a short little video on that. Now, I don't want to give myself lots of work to do, but if there were particular things within the thing, because I know people are coming from very different backgrounds, and we've seen questions there about why 0 to 255 and things like that, which are very obvious to certain people from certain backgrounds, and make they make absolutely no sense to people from others. So if there are little things like that you haven't come across before, firstly, number one to do is look those up on YouTube or in Wikipedia or whatever, and see if you can find a fairly simple answer. You can ask me as well. I may be able to find resources for you a little bit easier. Different little short YouTube videos. I may have some of them myself from my old computer programming modules and things like that. So don't be afraid to ask what you may feel are silly questions, because oftentimes they can be more crucial than some of the notes that I'm giving you here if you don't know them at all. What I would ask people to do as much as possible is ask your questions on the forum, and ask them to everybody rather than just to me, because oftentimes it can take me a day or two before I can get around to answering all the questions on the forum, and the other students in the class will often know the answer. They'll be able to give you a very quick answer, and I'd ask you to do that if you do know the answer to a question. Don't decide not to answer a question on the basis that you're not 100% sure. Okay, if you haven't got a clue, don't be going answering the question. But if you're 70 or 80% sure that you've got the right answer, that's enough for me. I will still read the forum posts, and I would prefer that you gave your attempt at answering somebody's question than leave it for me several days later before I get a chance to answer the question. You will still help the person out by doing that. You'll also help yourself out. So as well as that, when you ask a question that you may feel is foolish, you're given the opportunity to the other students to answer that question. And one of the major things, if I go back to my very original slide here, something that I didn't really say, but is one of the major jobs of, I said that, an engineer really has to be very aware of both the maths model, the computer model, but the difference between that and the real world. The other thing that an engineer really needs to be able to do is to communicate that information. So every opportunity that you have to communicate what you know, you should grab it, and you should also give other people the opportunity to communicate what they know to you. So don't be afraid to ask questions. I think most people in the class, they will be from a background where there's other things they don't know, and later on you may well be able to help them. So make sure you do ask those questions off everybody, and if you see a question that you know the answer to or you're pretty sure of, do make an attempt to answer it. I'd like to see a lot of communication between you. I always know a class is working well if I see a lot of interaction on the forum. Okay, I'm going to leave it at that for tonight, guys, unless there's any further questions, and obviously, as I say, you can always ask questions on the forum as well. That's no problem, Colin. So Olivia's just asking about any recommendations there on where to get started with Python. I haven't put much thought into it because I've had to do this myself in the past, and I've picked it up from different places. So I've normally there would be particular editors and so on that we'll use. What I might do is I might get a chance to look at that tomorrow morning and send out a few pieces of information. In the meantime, I know that there's some of the students who maybe had no programming background and were maybe advised to go and do some Python programming or that. So some people may have much more recently than me had to set up environments and things like that. If you can do that. Put that up on the forum and help people out as regards where to get started. But certainly, Olivia, once you get a Python environment set up, you can pretty much type in any of these things into Google and you'll find an OpenCV version that somebody has already done and a program there. And I'm happy enough for you to use those rather than reinventing the wheel. Vin is asking, would C++ be okay? It is okay, but what I would say to you is you're going to end up, even if you're more expert in C++, and I was very expert in C++ in my time. It's been a long, I haven't done as much in it more recently than I have in C, where I would be very expert in C and not so expert in Python. But the thing is that if I want to go doing things with images, I can do things in 3 lines of Python that are going to take me screenfuls into either C++ or C. So then my recommendation would probably be that you tackle Python rather than sticking to C++ if you already know it. I don't mind whatever way the results come to me, but particularly if I'm going to put you into groups in assignments later on, there's a bit of an issue there if one person is working in C++ and the other is working in Python. So that's why I'd really advise you to make things easier on yourself. Give Python a go. If it really doesn't work out for you, go back to C++ certainly, but I would give Python a go. And Python's one of those programming languages you really don't have to be expert in it. You can just pick up things as you go and start pulling in different programs. There's a huge amount of people share their work in Python, so it's very easy to get your hands on. I'll just hang on before the recording ends, and just if anybody has any further questions that I'll answer. Yes, so Niall is recommending there that Udacity have a course on learning Python, and I did the intro to self-driving course on Udacity, and they actually had in different places different resources for setting up Python environments, so I reckon they have it. End is recommending Spider is a good idea for Python. What is the one I use? I can't remember. I've forgotten the name of it. It's a fairly fully fledged one, but I'll see if I can find it here. There's one called Atom, which is very simplistic. PyCharm. Yeah, Maurice is after writing it in there, because I think that's the one I recommended to you, Maurice, when you were doing the work on YOLO. Was PyCharm. Okay. Oh, there's a plugin for Eclipse IDE as well, so that's great. Maurice, I may have even given you some instructions for PyCharm. I can't remember. If I did, will you search them out and put them up? I think I gave you instructions for YOLO rather than PyCharm specifically, but there might be something in there on setting it up. I can't remember. It's a while. Yeah, check, and if it is there, maybe just send that up for everybody else and let them know. If I have done it, I probably have that document myself, but I've long since forgotten. Okay, I think that's it for the questions. So it's great to meet you all, and hopefully you'll learn lots from this course. It will be very challenging, but hopefully you'll learn plenty from it and enjoy it. Okay. So we'll stop the recording there at that.